that function is said to be a metric. Now the problem is that if you take any metric as a dissimilarity measure, then none of them will give you a metric between sets. None of them will give you a metric between sets. Note that we have distances or similarities between points. From there we have come to similarities between sets. Okay? So now, if you take your dissimilarity measure as a metric, then none of these things will give you a metric. So the next question is that, how do you define a measure which gives you a metric? Which is a metric? Well, there are some standard metrics available in the literature in mathematics. Okay, one of them is Hausdorff metric. Hausdorff metric. You can do Google search, you can do Wikipedia, you will find the definition. So you can use that for actually defining another similarity between steps. Okay? And probably these things you don't find in the general literature or text many. Okay? So this is what is the usual agglomerative clustering algorithm, which is what I discussed. Single link and complete link. So this is using distances instead of cosine similarity. If you use distances, this is some of the impact of the differences. This will give the difference between single link and complete linkage based cluster. Okay. Here you see this distance is smaller than these distances. So these two clusters are merged. These two clusters are merged. But here, the furthest point, this distance is larger than this furthest point. So, sorry. Yeah. So, this distance is larger than this furthest point. So, here these two are merged and these two are merged. So, this is complete linkage, this is single linkage. Group averaging, which is the second one that I mentioned, C1, C2. So those many similarity computations you need to do. Yes, bisecting k-means. This algorithm is very simple. What you do is that you take that cluster that has largest number of points, that you divide it into two clusters. You take the cluster that has the largest number of points, that you divide into two clusters. That is basically your bisecting k-means. That is, initially you start with a single cluster, that you divide into two by applying two-means algorithm. Now you have got two clusters. Find out the cluster that has the largest number of points. You take that cluster, that you divide into two, again by using k-means, by using two-means algorithm. Then you get three clusters. So in this way you go on doing it till you get k number of clusters, and then you stop it. That's known as bisecting k-means. Now this is the persons who are working in the usual data mining. This looks to be a sort of people won't be happy with this. The reason is that, I mean, you are assuming that the cluster that has the largest number of points is the one to be divided. Then you may have a question why that needs to be divided. Maybe you may have the largest number of points, but they can be very close. They can be very close, all the points can be very close to each other. But whereas the cluster with smaller number of points, they can be far apart. The points can be, the distances between them can be very, very high. So maybe that needs to be divided. How do you know that the one that has the largest number of points should be divided? Okay. That is the basic question. So, but the answer is that since the data set is sparse, you don't assume that your clusters are anyway so much closely knit. That is the basic answer. That's why people are using it. But then you can have your own reservations about this method, the same as I have my own reservations about this method. But since I am talking about clustering, and since this is one of the algorithms that people have already been using it, I have to tell this thing. That's why I am mentioning this. But then with this, I will also mention a few more things. In the usual literature on clustering, people don't do the division in this way. Do you know how they do the divisive method? One of the ways of doing, there are many ways. I will tell you one of the ways of doing is the following. You see, let us just say your data is 10-dimensional. Your data is 10-dimensional. That means you have points in, let us just say you have 100 points. Each point is a 10-dimensional vector. What you do is that for each one of the dimensions, you calculate variance. So you will have 10 variances. Since your data is 10-dimensional, you will have 10 variances. Find out that variable or that dimension for which the variance is maximum. For which the variance is maximum. Now with respect to the maximum, so now with respect to that variable, you will divide this data set into two parts. Let us say that variable number is say 3. The third variance of the third variable is say maximum. Then what you are going to do? You find out the mean of the third variable. Find out the mean of the third variable. Now you pick up a point in the data set, see the value of the third variable. If it is less than the mean, then this whole vector you put it on one side. If it is greater than the mean, you put the whole thing on the other side. So in that way you divide the set into two parts. Is the method clear to you? So this is a way in which people follow. This is a way which people follow. So what you need to do is that you have one cluster that you divide into two clusters in this way. Now from 2 to 3, how you will go? What you are going to do is that for each one of these variables you calculate the variance in each cluster. So you have 10 variables. So for one cluster you will have 10 variances. In another cluster again you have 10 variances. So totally 20 variances. Find out the maximum of these variances. That maximum, if it happens in cluster 2, that cluster 2 is to be broken. If it happens for cluster 1, then cluster 1 is to be broken. And then you divide that thing into two clusters in this way. So this is one of the ways which people follow. But then I started my whole lecture with on one point, the number of dimensions or the number of variables is more than the number of data points. So if your number of variables is say 50,000, if your number of points is say how many, say 10,000, then how many such variances you are going to calculate? For one cluster it is 50,000, okay, and if you have to make it into 10 clusters or 20 clusters, these calculations are going to be more and more. That is why, though this is the algorithm that I just now mentioned, is one of the standard algorithms for division in the usual pattern recognition data mining literature. These people are not following because your number of dimensions is more than, here you need to calculate too many such variances, which may be really highly computationally expensive. But then there is another one. If you want to divide the cluster that has largest number of points in two clusters, then that doesn't really satisfy many. So, you can have your own reservations about this method. That's basically what I wanted to say. Next. Buckshot. This is another method. Well, what you are going to do is that if your number of pages or if your number of documents is very large, you take a random sample from there. That sampled set of documents, what you are going to do is that those documents basically you try to get your representative points or the mean from those documents. Once you get the means from those documents by using, let us just say you have 1 lakh pages, you are supposed to do the clustering 1 lakh documents, then you don't go in for the clustering of these 1 lakh documents directly. You take, let us just say, sample of 1000 documents. Randomly you choose this 1000 documents, this you divide into the k number of clusters. And then you find the representative, you find the k mean. And then what you are going to do is that you use those k means as the starting point for the whole method. So, here you have many questions. The first question is how to decide the number of points. How to decide the number of points? It combines, you see, okay. Randomly take a sample of documents of size square root k. Run group average, okay. You are going to use the hierarchical clustering technique on this sample to produce k clusters. Then use the results of this HH as initial seeds for k. So here it is, that is you are going to use hierarchical agglomerative clustering for the initial grouping, and once you do that, you get the representative, use the results as initial seeds for the k-means method here. So basically for the choice of initial seeds, you are going to use this one. There are very many clarifications that need to be given here. The first clarification is you are supposed to choose a sample of size square root k into n. Now if I choose one such set of documents, I will get one such set. My friend here, he will get some other such set. And some other person, he can get some other such set. Now the question is that, will the results be same? That will be your first question, because whenever you are going to do some random sampling, you know that one sample is different, may be different from another sample. So the results can vary. So the question is that are the results going to vary? The unfortunate answer is yes. They are going to vary. It tries to avoid the bad seed selection problem. What is this bad seed selection problem? Look at the usual k-means clustering where you are starting with the initial set of seed points. So if your initial set is very bad, then you may end up with, you may not end up with good results. Okay. So in that way, it tries to give a way of choosing initial seed points on the basis of the set of documents that you have. So in that way, it is slightly better than what was existing in the usual k-means, but you still have sometimes the initial root k documents, this may not represent all the categories, where the categories are diverse in size. This usually in text mining problems, you may have some categories or some groups from which the number of points or the number of documents in that group can be very, very small, or it may be small compared to the other big clusters. So when you do the sampling, you may not get any representatives from each. That can happen. That can happen. Supposing you are trying to do some clustering of, say, documents related to some diseases. Okay? So you have documents related to several diseases. But then there are some diseases which are rampant, like, let us just say, sugar, BP. So probably you will find many pages corresponding to them. But then you might have some other diseases, very, very rare diseases, where you may have very few pages corresponding to them. So when you do the random sampling, the documents corresponding to those rare diseases, they may not be present. So these sort of things are going to happen. I mean, so this is one negative point. This is the negative point of the method. So I need to tell you this negative point. Oh my God. It's already 3:25. Issues related to cosine similarity. There are, let me try to see. This is something that I wanted to tell you. I don't know how much time I am going to get. 15 minutes. So a new similarity measure is introduced to overcome some of the problems related to the cosine similarity. It's basically, what we are going to do is that it's called as extensive similarity. Basically, the definition of extensive similarity has a few steps. The first step is that we define distance between two documents. The distance between two documents is 0, is 1, if the cosine value is a small value. If it is small or large, it depends on the value of theta. It depends on this theta. If it is greater than theta, then it is large. If it is less than or equal to theta, then it is small. So how to choose this theta, will come to it later. So if the cosine value is small, means the similarity is small. Similarity is small means the distance is large. So distance, we are taking it as 1. Otherwise, the distance between the documents, we are taking it as 0. Okay. So once we define this distance, then what we are trying to do is that we are trying to define extensive similarity between two documents. Note that when we are defining this distance, it is only corresponding to those two things. It doesn't correspond to other web pages or other documents in the corpus. Whereas when we are doing this extensive similarity, we also take into consideration what are the distances between these documents and the other documents in the corpus. So what we are going to do, we define the distance, extensive similarity between two documents under two situations: when the usual distance is 1 or when the usual distance is 0. When the usual distance is 1, that means the distance is anyway present here, then we call this extensive similarity as -1. That is, actually there is no similarity between them. But whereas if they are 0, then what we will do is that we calculate the distance of D1 with some dk, and with the same dk we calculate distance of D2. If these two distances are same for all such k, then actually the value of L is 0. If for some case they are different, then the number of cases for which the distances are different is L. So because the modulus value is either 0 or 1. If this is 0, then the difference is 0. If one is 0 and another one is 1, then the difference is 1. If both of them are 1, in fact, okay. So wherever these two are different, those are the things that we are going to take, and this summation k is equal to the number of documents for which it is different. That's actually right. Okay. So we are going to take the extensive similarity to be this, and this is basically the way, and this is one of the illustrations. I will deal with the illustration slightly later if I get some time. And the extensive similarity has this property. It is symmetric. D1 D2 is same as D2 D1, and it is not a metric because if D1 is equal to D2, then ES D1 D2 equal to 0. But then ES D1 D2 equal to 0, it does not mean that D1 is equal to D2. It can be 0 even in this situation. But it has other nice properties. Triangular inequality is satisfied for non-negative ES value. Triangular inequality is satisfied. And it is actually, we are taking the negative quantity minus 1 so that we don't put them into 2 in the same cluster. So, with this, a new clustering algorithm is defined. This algorithm is, it has, the basic principle of this algorithm is that it basically uses the hierarchical approach, and it puts the documents together if the ES values are, first you start with small values and then you go on increasing. The distance between nearest two documents becomes the cluster distance and is derived from extensive similarity. This is basically the definition of distance between two clusters. The definition of distance between two clusters is the minimum ES value between them, basically. It is minus 1 if all such values, I mean ES D1 D2 greater than or equal to 0, it cannot happen for any D1 and D2, then it is minus 1, that means all of them are minus 1. And it is 0, 1 or 2, when it is not minus 1, then it is either 0, 1, 2, 3 or 4, so the minimum of ES D1 D2. When ES D1 D2 greater than or equal to 0, D1 belongs to the first document and D2 belongs to the second cluster. So this is basically the extension of the usual distance. And so you go on joining the points, you go on merging the clusters when the distances are smaller. Like in hierarchical clustering. And this is the illustration. A histogram thresholding technique is used to choose the value of theta. Once you define the ES, extensive similarity between documents, then you just go on merging the documents to create the clusters, or you go on merging the clusters the way you do it in the hierarchical clustering procedure. You use the similar logic using the ES definition, and you go on merging them. But then, unlike the usual hierarchical clustering procedures, here you don't need to define when to stop, because whenever you cannot merge, then it will stop automatically. And there is a way, I mean, if ES D1 D2 is minus 1, you cannot put D1 and D2 in one place. So that minus 1 is the one that's going to suggest to you when to stop. You will go on doing the merging till you cannot do any more merging. That means at some place you are going to get that -1. Then you are going to stop. Chaining effect is not present. And there are some more salient features. Validity of document cluster. I hope all of you know about this book. Do you know about this book? Jain and Dupes. This is one of the standard books. The Jain and Dupes book, this is one of the standard books for clustering. And it talks about cluster validity in very much detail. It has around 3 to 4 chapters on cluster validity. The title of the book is Algorithm for Clustering Data. The authors are Jain and Dupes. I hope you know Jain and Dupes. Do you? Jain is Anil Jain, Michigan State University. And Richard Dupes, unfortunately he is not alive. He died a few years ago. He was his colleague. Both of them are in computer science department. And they wrote this book. And definitions: normalize mutual information. This is a way in which you validate your clustering, and there is this F measure, precision recall. Precision and recall, and using the precision and recall you are going to define F. These are some of the standardly available methodologies for validating the clustering methods. As I said in the beginning of the lecture, they are standardly available. It does not mean that they are the best and nothing better can be done. That is not true. They have their own limitations, and it assumes, note that, it assumes that you know the classification already. The class information is known. So if you know class information, you are doing your clustering and you are trying to get the validity of your clustering by using the class information. That itself looks slightly strange, right? That looks slightly strange. So it has its own limitations. It has its own limitations. So nevertheless, this is something that, this is a way in which you can validate your clustering. So these are the things that are used, and many text data sets. I hope all of you know by now some of these text data sets. You have 20 news groups, Reuters, and you have Carifis data sets, etc., etc. These are the data sets that have been taken, several data sets, and the method for clustering, you see the last column, it is giving the best results, and the place where it is not giving the best results, even that's also shown. Okay, this is by using F measure, and this is by using normalized mutual information. And the computational time is comparable with the other methods. Here note that there are something that I have not dealt with. I will KNN, K nearest neighbor method of clustering, not classification. And then there are SC and SCK. Those methods I have not discussed. But these are also some of the other methods for clustering. So this has been compared, and these are my final comments. Whatever methods that have been discussed, they are heuristic in nature. You need good amount of theory, which is absent. And the usual clustering algorithm may not always be applicable, since the number of dimensions is large and the data is sparse. Many other clustering methods like spectral clustering, non-negative matrix factorization, they are also available. In fact, they have been compared with this Qs, okay, but we have not discussed. There are bi-clustering methods. They are also available. And dimensionality reduction techniques will help in better clustering. Dimensionality reduction, feature selection is a very important topic. I don't have time to go through those things. If people are interested in, maybe in the tea break, I can discuss with some of you. The literature on dimensionality reduction techniques is mostly limited to feature ranking, though there are some other methods, but the general methods of dimensionality reduction, that's basically limited to feature ranking. And then about cosine similarity measure. I already mentioned about some other way of defining dissimilarity. And these are the references. And basically, T. Basu, CM Murthy, that is the Qs. That was the paper that I taught you in the last, that appeared in 2013, Journal of Pattern Recognition Research. Thank you. Field is open for questions. You have some questions. Yeah.
So I have two questions on this K-means and a comment. The questions are, how do you select the right value of K? Because you may be doing 2 means or 3 means like that, and what is the right value?
Right.
Second question is, you said that in the K-means clustering, spherical clusters are produced. So can this be proved from the algorithm description? So that is the second question. And the comment I have is that you said that so there is not much theory developed, only mostly this clustering is heuristic. So while this is true, but in recent years there have been a lot of